All right, so we're going to move quickly through the rest of the air control, and we're going to move into the control valve sizing stuff as fast as I can get there. Okay, so this slide's a little bit of a review. We talked about this. This is looking at air separation. And so oxygen and nitrogen primarily can be dissolved in water. And the lower the temperature, the more it can handle. And the lower the pressure, the more it can handle. So if we want to get it out, we have to heat up. I'm sorry, the higher, I misspoke that. The lower the temperature and the higher the pressure drives the nitrogen and oxygen into the water. And so to get it out, we heat it up or we drop pressure. Both of those will bring these bubbles out of solution. This shows what happens if you just take some cold water out of the water fountain and let it warm up on the table. Okay, and we talked about this quickly about the bends the other day. So when you're diving, you go down, say you go 50, 75, 100 feet, the pressure is much, much higher on the outside of your body, and that will force mostly nitrogen. The oxygen is getting used up by the body, but there's nitrogen circulating, and it drives more nitrogen into your blood and your tissues. Well, when you come up, that stuff has to come out. And if you come up quickly, it will come out fairly good-sized bubbles will come out, and those bubbles will cause pain. And if it's bad enough, it can cause death. So you have to be, they have decompression chambers, or you just have to come up at a specified rate. You go up to a certain depth and you wait 5 or 10 minutes, and you go up again and you wait and you wait. And then you go up slowly, and it lets all that come out nice and slow, and you don't have any negative consequences. But if you come up too fast, it's basically like you get these nitrogen bubbles floating around in your blood, and that's not good. Okay, so we know the point where a compression tank connects to the system is the point of no pressure change. That's important for air separation. That's where we want to separate any free air from the flow and get it into the compression tank. Okay, so effective air control, if you design a hydronic system, air control is a big deal. And so you have to take these 2 points into account. The conditions that affect the release and absorption of air in the water for all systems. So we need to understand that. So we know air is roughly 20% oxygen, and 80% nitrogen. If a system is closed, the oxygen will go away quickly by oxidation. And so it's basically nitrogen that you're left with that can circulate around in your system. Now, if you're continually adding fresh water to the system, if you've got leaks, then that's an oxygen source. But most people are able to get that stopped. So here's our curves, and hopefully you can read those. Basically what we have here is we have different temperatures down here on the x-axis, 50 up to, what is that, 300 as you go across. Every 50 degrees we have a line coming up. And then we have different curves for different pressures, 0, 5, 10, all the way up to 150 PSI, and that would be PSIG. And this scale over here, it's kind of interesting. It takes a little thinking about that. That is it's the nitrogen that's soluble in water expressed as a percent of the water volume if you took out the nitrogen and let it be at 0 PSIG, or atmospheric pressure, and 32 degrees. So it's kind of a expanded volume, but anyway, why they chose to display this in those terms, I don't know. But anyway, I mean, as far as we're concerned, for qualitative purposes, this is more and this is less. And so you can see if let's say you pick a pressure at 50, say you were at 50 psig. Well, over here on this scale at 50 degrees and 50, what are we? That's, was it 5? I'm getting lost here. 5, we're right here. So what is that? What's that, 8%? 5, 6, 7, that's 8%. Okay, if you keep the pressure the same and heat it up to 200, that's going to fall down here to, what, a little about 3.2%. Okay, so in boilers and stuff, when we de-aerate the feed water, what do? We heat it up. We typically, in a feed water heater, we typically get up to someplace between 230 and 250. And so you can see, you know, if you don't have much pressure over in this region, you've gotten not all of it, but you've gotten most of it. And then if you think there's oxygen in there on a boiler, then you have to put oxygen scavenger chemically to grab the rest of it, okay? Or you can say, okay, well, let me pick a temperature. Let's say I've got 200-degree heating water. And so you can see at 150 pounds, I'm over here at 10%. If I keep the temperature the same and drop to from 150 to 50, come down over here, I'm about 3.3%, something like that. So dropping that pressure at constant temperature will bring that nitrogen out of solution. Okay? So that's kind of what we're working with here, and the scale and the units may be a little screwy, but the characteristics are tell the tale here. And that's where it's just laying out in the slides what I talked about. So, yeah. Okay, air separation. Okay, so what we have to do, we have to design a system so that when the nitrogen comes out of solution, either by heating or pressure drop, it will be only at one point. That's your goal, but that's probably not going to happen all of the time. You're going to have to pick just the best point. And that's, as you put the system together, that's one of your design considerations. And that should be the point where we connect from the piping system to the compression tank. And of course, you need to be concerned about, you know, we talked about when we turn on a pump, do we get an increase in pressure or do we get a decrease in pressure? If we connect on the wrong side, we turn the pump on and we get a decrease in pressure, then that's going to pull nitrogen out of the system at those points of reduced pressure, and that may or may not be where we want it to come out or where we intend it to come out. So all of that has to kind of be coordinated. So this bottom bullet, pump should not be a cause of creating reduced pressure areas at remote points in the system where air can be released from solution and potentially lodging coils or someplace that would then make the system not function properly. Okay, so ideally, we want to have it at the point of highest temperature and lowest pressure. Yeah, but, you know, it's seldom, as it says, this is seldom possible. So the engineer has to do the best he can, and he needs to design the piping so that any free air in the system will get carried back to the point where it can be separated and eliminated. Well, how do you do that? Well, there's this kind of magic number, 2 feet per second is a number you need to remember. Because normally, if you have a velocity of 2 feet per second, that's adequate to pull air back through the piping in the flow to the point where it can be separated and gotten out of the system. So that's kind of a magic number. And so, you know, on one, you know, when you're designing a system for energy efficiency, you want large pipes and slower flow rates to reduce the pressure drop. But for air control, you see, as you increase that flow area, you slow down the velocity, and that's what causes the frictional losses to be lower. But if you're trying to return air to a point of separation, that's not so good. So you've got competing, that's what design's about. You've got competing issues here, and you have to chart a course that does the best that you can to satisfy all of the different interests of the system. One is air control, two is efficiency and not using any more electrical power to circulate than you have to. High points in the piping circuits, coils can be collecting points. So by proper pipe sizing, particularly downfeed, because what you have, say you've got some pipe up here, you got some air, and it's in the downfeeds that you have to particularly have the velocity. It's got to be fast enough that it can pull the air or the nitrogen bubbles back with it and get it back to your point of separation. So 2 feet per second is the number. We'll have some more on this in a second. So basically, if it's not possible to do high temperature, low pressure, you go for the temperature. Forget the pressure, go for the point of high temperature. That it's a larger impact on air coming out is that at the point of high temperature, you'll drag it out of the system better. Sometimes we have fairly high buildings, and we'll still do the air separator down in the basement because that's where the boiler is, that's where the high temperature is, even though you got static pressure sitting on top of it. Okay. Yeah. Okay, and so this is just an illustration. If you have, say you had water downflowing in a pipe, if this velocity is less than a half of a foot per second or 6 inches per second, that water can go down and the air will still rise, opposite to the flow, which is not what you want, because then you can't control it, okay? So if you're greater than 2 feet per second or greater, when the water comes down, there's enough, friction on the bubbles that it pulls it down with it, and so then you can move it to a point where you can separate it. So that's what that slide is getting to. Let's see. Okay, a boiler. Boilers are very good at separating air because what? They heat, and they typically have large internal passages where the velocity is pretty slow, and it'll let that air rise to a point where it can be separated. And there's one component that's used is called a boiler dip tube, and we'll show some pictures of that. But wherever that nitrogen or air is allowed to collect in the boiler, that's where we want to put some sort of a fitting so that we can then get it into the compression tank. And so the last thing you want to do is let this accumulate and then get circulated out into radiation. That means the coils and all, where it could block a coil. And so some manufacturers provide what they call these dip tubes with them. And so here's some different configurations. So we've got cool water coming back from a system. This is a boiler. And so we heat it up, and this is the dip tube. And so this tube has the ability to separate out air bubbles that come up here, get separated out and get sent to the compression tank. And the deaerated flow goes out to the system. So this is boiler dip tubes for top outlet boilers. Look something like this. For our side outlet boilers, sometimes the outlet will come out on the side, and that means basically the same thing. It's just a little bit of a different configuration. And then some boilers, boiler dip tubes for reverse flow boilers. And so you see here, we're coming back with a cold water in here, and we're having to separate really before we heat it. So this is not ideal at all on this situation. And so here, at least this is collecting in from inside the boiler, and so that can rise up and get separated. So it depends on the boiler, the configuration, so there's different possibilities. Okay, and then there's different types of air separators. Say maybe you don't have a boiler, or maybe the boiler is just not practical to try to do your point of air separation at that point. And so there's what they call the IAF separators. And this basically is a fairly wide diameter tank, and it has a dip tube in it. And so the flow comes in, and I think usually these things are set up a little bit tangentially so that maybe you get some swirl in here. But anyway, it comes in, and then the flow has to reverse and has to go down to the bottom of the tank and reverse and come back up through here. And so the residence time, and because of the diameter, it slows it down. It lets the bubbles come out, and then it rises up to a dip tube type fitting here where the air is separated and sent to the tank. So again, tests show that water must be slowed to at least 6 inches or a ½ foot per second. Low velocity air separating tank equipped with dip tube. So I think we pretty well said that. So anyway, this is a slowdown in the flow and an air reversal that helps to separate. This is a fairly cheap device, but it's not necessarily the best. There's some more stuff, just talking about the geometry, vertical distance. Yeah, there's nothing there. It has a drain valve. You know, this is also an opportunity for any particulates or anything in the system to fall down where they could be removed at the bottom of that tank. And then there's the Rolairtrol Air Separators. So these are kind of a vortex type device, and they have a screen in here. And so this stuff that comes in, these connections are over on the side, and they make this stuff swirl around. It's kind of like a centrifugal air separator. And so the portions of the water that have air bubbles are lighter, and the heavier, if the water does not have air, it's lighter. And that centrifugal effect, the denser water without air goes to the outside, and the lighter accumulates in the center. And then they put this screen in here, and the screen helps to pull the air through. It provides another little pressure drop. It gets the air through, and then you can separate it out here, and then the deaerated water goes out the other side. So with the air and nitrogen comes out the top of this thing. So that's a Rolairtrol. That's a centrifugal type device. There's a description of it. Well, that's, I guess, compression tank installation. Separated, and it says free air rises into the tank. Okay, an equal volume of water must be replaced and returned to the system. So systems usually have a way, we'll have automatic air vents. We'll see some diagrams of systems in a little while so that you can control, because if you let more water go up into that tank, then you can change pressurization, and that can be an issue. As far as tests show that 3/4 inch diameter is the smallest that you should use. And we have a table here that gives some recommended pipe sizes in connecting these things. So this could be an air separator or a boiler, something like that. And so total length of horizontal connection only. So this is just the horizontal portion of this, up to 7 feet. And it depends on which fitting. You know, Bell & Gossett has a couple of different fittings. If you use the 3/4 inch fitting, up to 7 feet, you can go 3/4 inch pipe. If you go up to 20 feet, 1 inch, up to 40 feet, 1 1/4 inches, and up to 100 feet, 1.5 inches. So that pipe has to be big enough to accommodate the air and any water that's moving back and forth. You can see that. And so sometimes if you're limited on ceiling space, you can't have one tank big enough. You have multiple tanks. You may have 3, 4, 5 tanks that are smaller diameter that are mounted up on the ceiling, and they have to be manifolded together, and then they operate essentially as one tank. Okay, that's kind of a nifty trick if you don't have any ceiling space. And so this shows you the manifold sizes for multiple tanks, 2 tanks, up to 4 or 5 or more tanks. So make sure that piping is right. We've talked about the Rolairtrol fitting before, so I won't say too much about this. This is the one that passes air bubbles into the tank and eliminates gravity flow. This can be hot, and it keeps the air and water in the tank cold. If this gets hot too, then the pressure increases, and that requires a larger tank. So we've already talked about Rolairtrol fittings. And that's just our kind of general system diagram that we've seen before. So there we go. And we are finished. Yay. That presentation. Okay. So let me pull up this other one I gave you today. And some of this is redundant, but there are some diagrams and some other things in here that so JM Pleasant's company, they are a distributor, a sales house out of Nashville, and they have some very excellent people that do seminars, and they train the engineers in and around Nashville on how to properly apply some of these components and design concepts. So they're pretty good. So expansion tank, I put this in just to show some pictures. This is just a plain steel tank. This is a bladder type tank, and we'll have some more pictures in a second. So this is kind of what we've referred to in the past, but they also make bladder tanks, and this thing will have a heavy duty rubber bladder in there, and you can pressurize. They pre-charge this. The air around the outside of the bladder, they pre-charge to 12 psi at the factory. When you employ one of these, the idea is you set the air pressure so that when this thing is in the system and the system is full, before you heat it, that this thing has just almost no water in it, so that you have the entire bladder area to expand, for the water to expand into. And so depending on where you put it in the system, it's going to see a different pressure level. And so you have to set the pre-charge pressure in this correctly so that you get the full use of the tank upon system heat up. So the standard number is to just pre-charge this to 12, and they do that at the factory. But if you need 20 on your installation and you don't pre-charge it, then this thing is going to be partially full of water before you start heating up the system, and it'll be too small. So this pre-charge pressure is a big deal on these bladder type tanks. There's just more. I think that is that the Series B. The Series D, that's to 2 11 gallons. This is to 3,900. So just different size range. Same basic thing. And these are bladder. They also have bladder tanks. We've looked at that. We've looked at that. There we go. Let's look at this one for a second. So this shows the bladder, and this is the air pocket that gets pre-charged to the desired pressure. So these bladders can be changed. It's not a lot of fun, they say, but if these get a tear in them, you don't have to throw the whole thing away. You can take this apart and wrench this bladder out and replace it. The diaphragms cannot. They are affixed. If this diaphragm tears, then you got to get rid of the tank. So obviously this is cheaper than this, but this long term will probably save you money. Same sort of a thing. Both of these are pre-charged to 12, but should be adjusted in the field to whatever the installation needs. Why do we need thermal expansion? We know that. We've been over that. Okay, so here's, I thought this was kind of a nifty little example. And so this is showing, you know, a 90-foot building. Okay. And so the static head on the building, what? 90 divided by what? 2.31 is 39 PSI. Okay. So if you just put a pressure gauge, if you have a column of water that's open, put a pressure gauge, you're going to see 39 PSI. But now they say, okay, with the pump off, we got 43. Why is this 43 and not 39? Is that a mistake? Anybody? That's our minimum cold fill pressure, because we want 4 PSI minimum cold fill pressure at the top of this thing. So that's the other 4. Okay, so we turn the pump off, everything's sitting there, and, you know, so this is like cold, because it hasn't expanded. We haven't driven up pressure or anything. We just have the static head plus the 4 up here on top. And, okay, but now look, this is, where's our point of no pressure change? Well, it's up here, right? Because that's where the compression tank is. That's where all this stuff hooks into the piping system. So this is not right. So when I turn this pump on, it's pumping this way. So what's going to happen on the pressure on the suction side? It's going down. And the pressure on the discharge side is going up. Well, is that going to cause a problem? Well, what's the potential problem it could cause? Cavitation, right? We're concerned, well, it could do other things. You know, if the pressure is low enough, it could pull air into the system. It could separate air out of the system, you know, so we'd have to make sure we have our velocities right. But the other problem is cavitation on the pump. We got to make sure that we still have enough pressure at the suction of the pump so that we don't cavitate and tear the pump up. Okay. So then he says, okay, well, let's turn on the pump. Turn on the pump. Tall bill, oh, come on. Okay. So now the pump, 140 feet is what the pump's designed. So how much pressure is that? 140 divided by 2.31. So that's 60. That's basically 60 pounds of pressure. Well, so he says, I've got 13 here and I've got 73 here. Well, 13 and 60 is 73. So I'm getting my 60-pound increase across the pump. Now, because my point of no pressure change is up here, I'm now, instead of 43, I've taken 30 pounds off of my pump. Is that a problem? How would you know if that was a problem? What would you do? Yeah, you go check your pump and see if the pump can operate successfully with 13 psig at whatever temperature this water is, if that's going to cause a cavitation issue. Okay. The other thing, notice that, so this one goes down 30 and this one goes up 30, because this was 43. And so what he's saying for this little example, this 60 pounds, he's putting 30 pounds of the drop over here and 30 pounds of the drop over here. So he's splitting it down the middle. Now, in a real system, there would be no guarantee that it would split like that. You know, I mean, what if that pump was way over here? Then you would have less drop on this side and more drop on this side. So depending on the characteristics of the system. There's nothing to say that this 60 pounds is always going to split 30 on this side and 30 on this side, which is what he did in the example. Okay, PRV location. I don't think there's any. Yeah, we've looked at this for the, you know, that's where our fill is on the system. Okay, well, okay, so this is where you're supposed to do it, right? So this is the compression tank. This is my cold water line coming in. This is my pressure reducing valve that's set for 12 PSI over here on this side of the system. And this is on the suction side of the pump. That's all the way it's supposed to be. What happens if you put it down here? Does that look right? Put my fill line down here with a set point of 12 PSI to feed water into the system if the system loses water. I've got 12 pounds in my compression tank. This is my point of no pressure change. When I turn on the pump, what's going to happen to the pressure at that point? Going up. Is that a good place to tie this line in? That ain't going to work. That dog won't hunt. Heavens no. So pump pressure increases to 26. This thing could drain a lot of water out of this system before this put any water back into it. So see, this has got to be tied in over here, tied into the point of no pressure change that's then controlled by the compression tank. That wouldn't work. Well, we've seen that. Okay, so this is just some Series B tanks. I think these are bladder type tanks. Okay, so let me say, okay, so he's going to select one. Yeah, he's going to select one for this system. So it's got 2,000 gallons at 40. We're going to heat it up to 180, so it's going to grow by 56 gallons. Okay, so well, here's, and the tank, the acceptance volume is what you really design for. Some of these, sometimes they're different, but that's how much additional water can it accept. So, okay, so this is 80. This is 80 gallons. This is okay. Well, it's going to go up 56. Select an 80. Should be good, right? Let's see. So there's my system. So we start out with 2,000. We heat it up. It goes up to 256. Here's my bladder tank. And so you can see kind of here's my situation. He's got his point of, he's got an actual air separator in here, not just using the boiler. So this is like a Rolairtrol separator. And with the Rolairtrol, he's putting an air vent on this thing that will vent as on system heat up. A lot of air comes out of this thing. It will feed into this tank and it will actually vent air out of the system here. And then it goes, this is the expansion tank right here. And here's the pump. He's got it tied in on the suction side of the pump. So that all looks pretty good. We're going to pick up 56 gallons upon heating. Got an 80-gallon tank. What could go wrong? Well, let's see. So let's just take a look for a second. So 80 gallons of air in the tank, 12 PSIG, which is 27 PSIA. We're going to do a little ideal gas law stuff here. So we got to get to absolute pressure. Boiler's off, 40 degrees. Okay, so boiler's on. System volume is 2056 at 180. So I've got 56 gallons of water in the tank, which leaves 24 gallons of air. What happens to the pressure? Well, we're engineers. We ought to be able to calculate that. So we can use Boyle's law. So here you go. So say we're assuming the temperature in the tank stays the same because we have the proper fitting on it. whereas it expands, but the temperature is the same. So we can, if the temperature is the same on both sides, it cancels out. So P1 V1 is P2 V2. Plug in the numbers, 27. These are our volumes, and we get 90 psi, which is 75 psig. Well, okay. So is that a problem? Well, it depends. It depends what the relief valve is set on and where the relief valve is. Okay. Well, see, we see the relief valve is going to be on the boiler, and the boiler is basically right here. So we don't have any elevation changes to worry about. But we look down on the spec on the boiler, and it's got a 50 psi relief valve. Now do we have a problem? Yeah. I got 75 pounds in my system. I'm going to be venting water like crazy out of that relief valve. So it's too small. So we need to select, and so here's a calculation that's done. What's that pressure, final tank pressure going to be? If we go 106, it's going to be 43. If we go 132, it's going to be 32. So the next size up would be acceptable for this. There we go. Well, and I haven't, B&G has this free selection software, and we'll pull that up next time. I haven't gone back to it lately, but it's pretty nice. So it will select for you. I think we've been through most of this. Let's see, I think we get a picture of it. Glycol, yeah. So there is a screenshot of some of the software. So, you know, you can put in your information, and this will suggest different tank settings, sizes and selections and all for you. Okay, I think that's pretty good. I know we got career fair, so let's go ahead and quit for today, and we will finish this off next time, next Tuesday.